you very much. Thank you for the invitation to speak here. Today I want to tell you about the quasi-symmetric flag variety. This is kind of a culmination of a lot of work that I've been doing with Vasu Tewari, Nantel Bergeron, Gagnon, and Philippe Nadeau. And to tell you what the quasi-symmetric flag variety is, I have to tell you the problem that it ultimately is going to solve. So first of all, I want to tell you about this special class of functions called quasi-symmetric functions. So symmetric polynomials. So I'm always going to work with polynomials because I'm going to be working with n variables. So we have symmetric polynomials. They're going to be contained in this mysterious ring of quasi-symmetric polynomials, which in turn is a subset of all polynomials. So I hope everyone's familiar with symmetric polynomials. I'm not going to say the definition, but I do want to say the definition of a quasi-symmetric polynomial. So quasi-symmetric polynomials have a couple of definitions, and they're all really confusing because it doesn't look like a very algebraic ring. So how you can define a quasi-symmetric polynomial, or one way you can define it, is that you want the fact that if I extract the coefficient of x1 to the a1, x2 to the a2, through xk to the ak from my polynomial, this is exactly the same as extracting the coefficient of xi1 to the a1, xi2 to the a2, xik to the ak, whenever I1 through ik is a strictly increasing sequence. Okay, so if I cover up this word strictly increasing, this is just an exhausting way of defining what it means for a polynomial to be symmetric. A bunch of coefficients are the same, because when I permute the variables, it permutes the coefficients. Strictly increasing here does something very strange. So I want to write down an example of quasi-symmetric polynomial for you. So this is going to be in 4 variables. I'm going to throw on some extra thing. Oh, okay, so here is an example of a quasi-symmetric polynomial. So just like the monomial symmetrics obviously generate the symmetric polynomials, you just take the orbit of a monomial under the symmetry you desire. Here, a quasi-symmetric polynomial, maybe I'll put a coefficient for fun. Here, a quasi-symmetric polynomial breaks up into these pieces where we group them together according to this condition here. So notice that the exponent sequence is 2, 1 in all of these, and the indices are strictly increasing. So the difference between symmetry and quasi-symmetry is that with symmetry, you would also demand, for example, x1, x2 squared. But here we don't require that. So quasi-symmetric things naturally break up symmetric polynomials because the monomial quasi-symmetrics naturally break up the monomial symmetrics. So if I had added on the similar thing where 2 and 1 were switched in all of these terms, we get the monomial symmetric. And then here, you can see that this quasi-symmetry condition is especially weird if you've packed all of your variables in, because then this condition is actually vacuous. There are no interesting strictly increasing injections from 1, 2, 3, 4 into 1, 2, 3, 4 other than 1, 2, 3, 4. So this monomial can just sit here, and we don't require any other monomials to save it with respect to this definition. Okay, so quasi-symmetric polynomials form a ring, and this is a very surprising fact given how weird this definition is. This is actually not a very nice ring, the quasi-symmetric polynomials. I don't think the ring structure is really understood in the finite cases very well. But there's an equivalent characterization of quasi-symmetry, which makes it very obvious that it forms a ring. So I'm going to define an operator on polynomials, which I'm going to call the Bergeron-Sotile operator. So the Bergeron Sotile operation. And it's going to do something very interesting, or not interesting, depending on what your point of view is. What it's going to do is it's going to stick 0 into the ith variable, and then it's going to reindex all future variables back by 1. So in other words, it's stick 0 in, and then make sure your variables are drawn from the set 1 through n minus 1, rather than leaving a gap where you stuck the 0 in. Okay, so quasi-symmetry is equivalent to the condition that all of these stick in a 0 and reindex maps give you exactly the same thing. So we can view this monomial equality condition as being exactly the right condition needed, so that no matter which variable I set to 0, once I squish everything back in, I'm going to get the same answer. So of course this, the form of this operation is naturally preserving some kind of total ordering on the variables, and that's being reflected in the total ordering on the strictly increasing sequence inside this condition here. Okay, so we have quasi-symmetric polynomials, and a question that we're going to be answering is about what's called the quasi-symmetric coinvariant ring. So I'm going to write down the question and then tell you what the classical answer is, which is extremely nice, then tell you the answer here, which is, I think, also very nice. So we're going to look at the quotient of polynomials in n variables by the positive degree quasi-symmetric polynomials. And we're going to ask, is this the cohomology ring of something? The symmetric analog, as we'll see, is the cohomology ring of something extremely nice. And basically, back in 2002, my collaborator Nantel Bergeron and his brother said, why don't I just stick a Q in front of this sim and see what happens? And they found that this ring had a lot of extremely nice properties, but not necessarily all of the nice properties that you would want. So, for example, when n equals 3, let me tell you what the Betty numbers of this ring are. So I'm going to tell you, so in degree 0, what's the degree, how many polynomials are there, modulo this relations. Degree 1, degree 2, there's actually nothing in degrees 3 and higher. So the degree 0 dimension is 1, these are the constant polynomials. Degree 1 dimension is 2, because there's, it turns out that, well, you have x1 plus xn in here, so that decreases the, the number of linear forms by 1. And then degree 2, it's 2, and then in degree at least 3, the answer is 0. So unfortunately, you can immediately tell that this was a bad question to ask. Bad question. Because, why is this bad? Can someone tell me why this precludes me from solving this question?
Maybe it's something not smooth.
Yes, maybe it's something not smooth. But if it is smooth, what is bad about the sequence 1, 2, 2? It's not symmetric, and it's not, oh, that's the one, yeah. Not symmetric and not unimodal either. So it fails all of the, standard things that I would think. But maybe it's not smooth. You're right. So that's one way it could happen, is it's not smooth, and it's a very scary not smooth thing. But there's another way that this can be solved, it turns out. And it could be that the variety is reducible. So what I want to tell you is a reducible variety whose cohomology ring is exactly going to compute this. But first I'm going to tell you the classical answer of the flag variety and some highlights of that, just kind of sum it up because a lot of this has been gone over before. So the flag variety.
So is it easy to see that it's finite dimensional array?
Yes, because it contains the symmetric coinvariants. So it's a quotient of the cohomology ring of the flag variety. Okay, so the flag variety, as has been said before, are the matrices modulo these upper triangular matrices that we've seen before. And this can be viewed as flags of subspaces, UN minus one, and where the dimension of VI is equal to I. Okay. So the flag variety has a very nice cohomology ring. It's generated in degree 1 in degree, I'll write 2, I guess, because technically they're in degree 2 because everything is complex, but I don't want to deal with that. So it's generated by some line bundles that naturally exist on the flag variety. These are the Chern classes of the consecutive quotients of, the tautological flag of subspaces. Doesn't matter. This is generated by some line bundles. Modulo symmetrics. So the flag variety's cohomology, it turns out that any symmetric function in these x's is equal to 0, as long as it doesn't have a constant term, because obviously 1 is not equal to 0. Okay, so in order to solve this question, I need to tell you, I guess, a way that you can show that the cohomology of the flag variety, that all of these elementary symmetric functions in the x's are equal to 0. Now, the usual way you would do that is you use like algebraic geometry, and you would say that they're like the Chern roots of the trivial bundle and something. I want to take a different perspective on the vanishing of all of these symmetric classes, which is going to naturally account for how you could possibly get quasi-symmetry appearing at all in any context. So here is the perspective. What we're going to do is we're going to look at the flag variety as acted on by diagonal matrices. Diagonal matrices. So here, the diagonal matrices in GLN act on the flag variety because I can just act on it because it's a subgroup of GLN. And we can look at certain invariant data of the flag variety with respect to this torus. So first of all, what are the flags that are fixed by the torus scaling? So we need flags of subspaces so that if I scale any coordinate direction, it doesn't change what any of the individual subspaces are. So a moment's thought should hopefully convince you that what these look like are, so the T fixed points are of the form permutation matrix, times B. So these are the flags associated, these are the coordinate flags. So they're just flags where each subspace in your flag is spanned by some coordinate vectors, and then scaling those those standard basis vectors aren't going to change the flag. So let's draw what these look like for n equals 3. So up here, I'm going to have the longest element, and here I'm going to have the smallest element, and here. Oh my God. What? Oh, yeah, that's right. Yeah. Okay, under any convention, I was wrong. Fantastic. That's great. Okay, so let me fill these out. There's going to be a purpose to it beyond how fun it is to draw every single matrix like this. And 2, 3, 1. Okay, so we have 6 permutation matrices that are fixed. And it turns out that so the fixed points are given by these 6 matrices. And the curves that are fixed by the torus, so set-wise fixed, so if I scale this curve of flags, it preserves the whole curve, they end up, so if I let me write them in one line notation. So this is 3, 1, 2, 1, 3, 2, 1, 2, 3, 2, 1, 3, and 2, 3, 1. So the curves are exactly connecting two of these permutations that they're related by a reflection. So if two of the numbers swap, there's some curve that connects these things. So in this case, I guess it goes like this, 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 and then across like this and across like this. Okay, so we can view this graph as a as like the one skeleton of like kind of a decomposition of the flag variety into torus invariant things. I throw away all the, you know, dimension 2 and higher things, and I'm left with this Cayley graph associated to reflections. Okay. Now, the flag variety has this very nice feature that that this graph is so nice, and there's a very general theorem called equivariant localization, but I won't tell you what equivariant localization is really actually saying, because I don't want to define a GKM graph and a bunch of complicated things. But I'll tell you an important consequence of equivariant localization that explains the presence of these symmetric functions in sim n plus. So equivariant localization says that because my torus fixed points are these permutation matrices, we have the following facts. If f of x1 through xn is a polynomial, I'm going to take some polynomial and I want to see if it vanished. I want a sufficient condition for this polynomial to vanish in the cohomology ring of the flag variety. Then the sufficient condition is, so I guess we start with let this happen, and suppose we can deform f, I'll put a little tilde over it, so it includes some x variables, the same x variables, and some t variables, t1 through tn. Okay, so I'm going to deform it. So concretely what that means is that ti equals 0 recovers f. So I'm going to add some extra variables in to this polynomial that if I set to 0, I recover the original polynomial. So suppose we can deform it in such a way that when I plug in a permutation of the variables, t sigma then, t1 through tn, this is equal to 0 for all permutations in Sn. Here, the fact I'm doing all permutations in Sn corresponds to the fact that all permutations in Sn are represented as torus fixed points. And the fact that we're plugging in these permutations of the t variables into the x variables is just how you equivariantly localize things to torus fixed points. Okay. So there's some like big geometry going behind this statement, which in theory should allow us to construct elements of this ideal that we have to quotient polynomials by, and we'll see why symmetric polynomials are inside this ideal via this process. Actually showing that, you know, all this, that there are no more polynomials is kind of annoying, but let's just show that symmetric things are in the ideal.
Sorry, what's the result of the theorem?
And also you need f tilde there.
Then f of x1 through xn equals 0 in homology ring. Oh, sorry, I forgot the most important thing. The whole point of writing down all that other nonsense. This is like a game. You have a polynomial, you're like, how can I deform it so that it satisfies this magic vanishing condition? So let's start with something. So let's take x1 plus x2 plus x3. How can I deform this polynomial by adding in a bunch of t variables so that it will vanish when I plug in a permutation of the t's into the x's?
Minus t1, minus t2.
Exactly. So you can just take your original polynomial And if I subtract T1, T2, and T3 off, look at how great this is. When I plug in any permutation of the T's into the X's, this vanishes. Now, more generally, if F is symmetric, and I have f of x1 through xn, there's an incredibly simple way of deforming this polynomial so it satisfies the constraints of this theorem. Does anyone want to tell me what that is?
To subtract off the t.
Yeah, there wasn't a hard question. Xn minus f of t1 through tn. Great. So this is why, from the perspective of this graph, why the symmetric functions lie inside this ideal. I didn't tell you about why the edges of the graph are the complete data you need to run some combinatorial tool called Gressy-Koslowitz-McPherson theory. So I just drew them really because it looks nice. It's like a hexagon with some lines in it. So it's good. Cool. So the corollary is that sim n plus equals 0 in homology writing the flag variety. I need to work a little harder and get the whole batch. Because once I have symmetric polynomials are inside the ideal, then any multiple of the symmetric polynomial will also be 0. So you bootstrap up from just symmetrics to the ideal generated by the symmetrics, because it's a ring. Great. So now I want to tell you how we're going to play this game to win with quasi-symmetric polynomials. So I'm actually going to define it here because I'm going to draw this over here. Okay. So I'm going to define a family of permutations called nice permutations. So a permutation sigma in Sn is nice if it arises from 1, 2, 3, n by the following game. So the game is going to be this. I'm going to tell you the moves you're allowed to do, and then we're going to start the identity and do moves in all possible ways and see what we get. So the game says, if 1 is in the first position, I can swap positions 1 and 2. Okay, so that's the first thing I'm allowed to do, is if 1 is in the first position, I can swap 1 and 2. The next thing I can do is if 2 is in the second position, I'm allowed to swap positions 2 and 3. Etc. So the condition is if I is in the ith position, you are allowed to swap it with the next number over. And we're going to say a permutation is nice if you can get it from the identity permutation via this process. And I'm actually going to notate the nice permutations because it's nice as NCN, the nice permutations inside Sn. Okay, so let's do this. So we're going to play the game. 1, 2, 3. Where can I go from 1, 2, 3 playing this game? Just any. 2, 1, 3. Because I can swap 1 because 1 is in position 1. I can do a swap. Where else can I move to? 1, 3, 2. Yes. Notice I'm not allowed to go from 2, 1, 3 to 2, 3, 1. So actually here you're kind of stuck because there's no other adjacent transpositions you can do. All right, so 1, 3, 2. Where else can I go? Yes, 3, 1, 2. Because 1 and 3 are 1 is in position 1 here. Then where can I go from here? Sorry, what? Come on. You can go somewhere. All right, these moves are reversible. Oh. Sorry, buddy. Okay, that was great. And then you get stuck. You can't get to 2, 3, 1. So 2, 3, 1 is very sad. It's just sitting there, not really, able to be got from this nice permutation mixing process. Okay, so in order to explain what the quasi-symmetric flag variety is, I want to decorate this graph with a little bit more information, which is the Bruhat decomposition. So in addition to these being the T fixed points on the flag variety, these are also the origins of some affine spaces that decompose the flag variety. So in order to write down those affine spaces, so this is the Bruhat decomposition, GLN mod B is the disjoint union of BWB mod B's, and these are affine spaces. So to draw what those affine spaces are, you ignore everything below and to the right of any one, and you put a star in any place that's not below and not to the right of any star. So here, go like this, star, then here, two stars survive here, two stars here, and then here, right here. So the stars can be any complex numbers you want, and these are affine spaces of dimensions 3, 2, 2, 1, 1, 0. Yes.
Is nice dominant times W naught?
No. I'll tell you what nice is in a hot sec, but it is not that. No. I will accept more guesses for what nice things are at any point you want. It is very difficult to guess what nice things are, even knowing what they are for n equals 4 is very nice. I asked ChatGPT, it could not figure out what nice things were. But they are actually a very well-studied class of permutations, as some people in the audience will know. But not from this characterization. Okay, so every point in the flag variety can be uniquely expressed like this. So in some sense, I've drawn the flag variety in this very nice hexagon-y way. And now I want to tell you what the quasi-symmetric flag variety is. The quasi-symmetric flag variety is going to be obtained by deleting all of the not nice permutations. So we're only going to keep the nice permutations. Now, what does it mean to delete the non-nice permutations? We're going to have the quasi-symmetric flag variety is going to be the union of all T invariant subvarieties of the complete flag variety with fixed points, nice. It's going to be all of the T invariant subvarieties you can do with all the T fixed points nice. Now, in order to do this, it turns out that we also have to delete some of the curves as well. So we actually are, well, I'll tell you how to, so first of all, it's not going to contain this point or anything inside here, but I'm going to tell you like what the process is for getting this union here. So
on your top cell up there, you should turn one of those stars into a 0.
Yes, that is what I will do. I will turn a star into a 0. But I'll tell you how to turn the stars into the 0, maybe more algorithmically. So there are certain functions on the flag variety indexed by permutations in Sn called generalized Fluker coordinates. They correspond to the extreme weight spaces of the fundamental of like the dominant regular representation for the file group, but for GLN. But I'll actually just define it concretely using matrices because everyone likes matrices. So how this Fluker coordinate is going to be defined is we're going to take a product from I equals 1 to n minus 1 of the determinant. So I'm going to take submatrices of my full matrices, and it's going to use columns 1 through I, and the rows are going to be W of 1 through W of I. So if I have matrices of the form A, B, C, D, E, F, G, H, I, and I take W to be this bad point 2, 3, 1, then the generalized Fluker coordinate is going to be the determinant of column 1, row 2. It's this one. And then in the first two columns, we're going to take the rows 2 and 3. So it's going to be this determinant. So we take the product of these determinants. So this is D times DH minus GE. And what we're going to do to excise all of these bad points is the way you get the union of all the T invariant subvarieties that avoid some fixed points is you just set those generalized Fluker coordinates to 0. So we're going to actually define, here, let me put it over here. QFLM is the set of points, is the vanishing locus for all not nice permutations of this Fluker coordinate being 0. So in this case, there's only one not nice permutation, so I only have to set this subdeterminant to 0. And I just have to see what survives. What survives after saying the subdeterminant is 0. So first of all, why did I delete the entire chart associated to 2, 3, 1? So that was this one. So let's compute let's call this A and B. Let's compute the 2, 3, 1 Fluker coordinate according to this procedure. I'm going to get 1 times 1. That's where I get 1. So when you set this Fluker coordinate to 0, it's actually going to destroy the entirety of this chart associated to its index, because the subdeterminants it pick out is exactly going to be this permutation matrix, and ignoring these A's and B's and whatever else. So when we set it to 0, so when I take QFL3 to be everywhere where this Fluker coordinate is 0, this 2, 3, 1 Fluker coordinate disappears. And now inside each of these charts, we can play this game. We can set the 2, 3, 1 Fluker coordinates to 0 and see what happens. 2, 3, 1. This is identically 0 in this chart, so don't have to get rid of anything. This entry is 0, so it's identically 0. This entry is 0, so it's identically 0. 2, this is not 0, but this lower submatrix determined into 0. So the last chart to look at is this top one. And when I set the subdeterminants to 0, I get this entry times minus 1. So setting that to 0 literally just sets this to 0. Okay. So now I have a variety that is paved by affine spaces in exactly the same way that the flag variety was paved. But now the dimensions are 2, 2, 1, 1, 0, which exactly matches what I told you were the Betty numbers of the quasisymmetric coinvariant ring. So it's at least conceivable that this reducible variety would be the answer to this question, if only because of that extremely small numerology.
Why is it irreducible?
It's reducible.
Oh,
Yeah, this is reducible. Geometrically, what this looks like, just to let you know what survives after saying this Fluker coordinate to 0. There's a trapezoid over here that corresponds to a toric variety. And trapezoid in toric variety land is called a yes, or Herzeberg surface. There's another toric variety here, which is another trapezoid. So it's again a Herzeberg surface. Yes. And it looks like they overlap, but that's just because these are like the moment polytopes of things in the flag variety, and I can't draw things in 4 dimensions. So unfortunately, the most natural way you would draw these polytopes, they overlap. There's no geometric significance to this variety here. So these are 2 Herzeberg surfaces glued along 2 P1s that overlap in a point. So yeah. Not the nicest way I could glue two Hertzberg surfaces together, but it is a way I can glue two Hertzberg surfaces together. Any questions? Oh. That is a great question. I will tell you what I will only solicit guesses for nice permutations of 14.
No.
It's not
There are a lot of Catalan number many classical permutations though, so I don't think that narrowed it down at all.
Reading words of two-row tableau.
Yeah. Okay. Any other questions? Right. So let me tell you what the let me tell you how this deformation problem, like why the nice permutations have anything to do with quasi-symmetry. So how they relate is through the following definition. I'm going to say a polynomial in two sets of variables is equivariantly quasi-symmetric if it has the following property. When I stick Ti into the ith spot, and then I guess reindex. This is exactly the same as sticking it into the I plus first spot. I, Ti, psi plus 1, xn minus 1, T1 through T. Okay, so this is kind of a restricted form of symmetry. So usual symmetry says that a function is symmetric if I can always swap the values of any two adjacent entries. Equivariant quasi-symmetry is by definition going to be the statement that you can only swap the contents of two consecutive entries, provided one of those two entries contains its favored value. And its favored value is located inside this big list at the end. So the first variable can swap with the second if T1 is in one of those two. The second can swap with the third if T2 is in one of those two. And now let's see how this interacts both with the definition of quasi-symmetry and with the definition of nice. So here's the first observation. Equivariant quasi-symmetric functions map to quasi-symmetric functions by setting all the t's to 0. And why does that happen? Because the definition of the alternate definition of quasi-symmetry was it doesn't matter where I stick a 0 into this list, I always get the same answer. So from that perspective, there's a very nice map like this, which is good. It's very similar to how the deformations of symmetric functions map to the symmetric functions by setting the t's to 0. Not obvious this is surjective. There's a big 50-page paper where we actually show that every quasi-symmetric function can be deformed to an equivariantly quasi-symmetric one. That's incredibly not obvious. There's no simple trick. And it's not the case, so I'll remark that this is actually a surjection. But what I'll remark is that EQSym is not the same as taking symmetric things and just multiplying them by polynomials. Q7 times polynomials. So it's not like I can find a deformation by just cleverly adding quasi-symmetric polynomials in lower and lower degrees to like fix problems. You only get quasi-symmetry in the highest degree, and then everything else is just true garbage. But you know, in totality, this is a very nice class of things that surjects onto the quasi-symmetrics. This is a ring like the quasi-symmetrics. Why are the quasi-symmetrics a ring? Is because quasi-symmetrics are the equalizers of these algebra morphisms called set a variable to 0. And here, the equivariantly quasi-symmetric ones are also in algebra because this condition respects multiplication. Obviously, if two things satisfy it, the product satisfies it well. So how does this interact now with the definition of nice? Well, by construction, equivariantly quasi-symmetric things take the same value on all nice permutations. Because my ability to play this game successfully gives me a certificate that the evaluation of that permutation of the t variables, when I plug it into the x variables, can be reduced down to the identity permutation. Any two of these evaluations are the same. So fortunately, because this is surjective, which is again an incredibly not obvious fact, the corollary is that QSIM is contained inside the equals 0 in this homology ring. And then you have to do some more work to show that it's equal, and part of that is basically a dimension count based on geometry, or there are other ways of doing it. But this is why quasi-symmetry is appearing with respect to those nice permutations. So now I'm going to tell you what a nice permutation is. So I'm going to tell you it in a let's take a nice permutation is the product of backward cycles on a non-crossing partition. Non-crossing partition of 1 through n. So for example, here is a non-crossing partition. Non-crossing, in this case, so here my notation for a non-crossing partition. This is the non-crossing partition 1, 2, 6, and 4, 5. So non-crossing means that the one part can't have two things and the other part is two things that interleave. You have to be nested one way or the other, or disjoint. So backward cycles on these things. So in this case, this is the permutation. 6 goes to 2, goes to 1, 5 goes to 4. So those are the nice permutations. So in other words, they're the non-crossing partitions, not the algebraic non-crossing partitions, for the Coxeter element associated to the backward cycle, and n-1, n-1. I won't go into what the general theory of algebraic non-crossing partitions is, but suffice it to say this works in any Lie type, and this whole story extends to any Lie type, and it all works very nicely. Right, so these are the algebraic non-crossing partitions. So the theorem that we have, I guess, is that that these algebraic non-crossing partitions is a union of the positive Catalan number many toric varieties. And each of these toric varieties is very nice. It's a translative or Richardson variety that you've seen before. But I want to end by actually telling you one incredibly interesting fact about these charts that we see here that generalizes to any type that might interest some people who are interested in clusters.
Are these part of Richardson varieties all smooth?
Only for this, in the case I described, they're all smooth. Yes, and there's an associated Schubert calculus that we created that uses in a critical way that these things are smooth, but only in type A for this particular C. Okay, so what are these charts? So let me show you how to take this cycle and produce one of these charts. And then I'll end there. So we have this product of cycles, and I'm going to describe the affine chart at this torus fixed point inside the quasi-symmetric flag variety. So I need two pieces of data. One of them is this permutation, which I have, so that's good. 5 goes to 4. So in cycle notation is this. So I've already told you how to create this piece of data. But now I need to tell you what stars are going to survive. And to tell you that, I'm going to create a cluster associated to this associated to this permutation. So first, I'm going to create a tree out of this permutation. So basically what you do is you take the unique tree so that if I delete these edges, the support of the resulting structure is the same as the non-crossing partition. So in this case, if I delete this edge and this edge, I see two things supported on this 5,4 and this 6,2,1. So I have the tree. And now I take the spreads of the tree.
So how did you know only to read out those two edges?
Because this is the rule that if it looks like a lambda in this orientation, you cut that. So then I'm going to take the spreads of the nodes. So I'm going to go as far down and as far to the left and as far down to the right. And I'm going to, for each of the nodes, I'm going to draw an arc that describes this. So this is called a non-crossing alternating forest for one of the obvious reasons. Non-crossing alternating forest. E1, E2, E3, E4, E5, E6. And these tell me what the roots are. E1 minus E2, E3 minus E6, etc. So this is a cluster. It's a type A cluster with respect to that Cox center element in the sense of Foman's elemency. Associated to this cluster, we can consider the unipotent subgroup that I get by putting stars in the locations of those inversions. So there's a star on 1, 2, a star on 1, 6, a star on 3, 6, a star on 4, 6, and a star on 4, 5. And conveniently, this definition was rigged so that if you draw things going up and to the right, it's just combinatorializing this tree in the dumbest possible way. So the chart is obtained by multiplying this permutation on the left of this chart, and this is the cluster that Biane associates to a non-crossing algebraic partition. So this works in any type, and there's a very similar story, and that's all I'm going to tell you for now, because I don't want to tell you anymore. Questions for Hunter?
Yes, sir.
We're careful to state that corollary as just saying that QSIM plus vanishes there, so this only gives one inclusion.
Mhm.
Is it actually true that we just quotient by that thing and then you get called the cohomology?
Yes. So if I quotient the cohomology of the, if I quotient polynomial rings by this ideal, you do get the cohomology ring of this complex. So this does solve the problem that's stated at the beginning of what algebraic variety has the cohomology ring being the quasisymmetric coinvariants.
No torsion.
No torsion. No, and it's because of this affine, complex affine paving, it prevents any torsion from occurring. Yeah.
Can you do the torus equivariant cohomology of this?
Yes. So the torus equivariant cohomology of this is given by polynomial rings in the two sets of variables modulo these equivariantly quasisymmetric polynomials. So this is ultimately why we introduced it, because we wanted to basically copy the Schubert story. It turns out this definition is rigged so that if you write down algebraic proofs of everything you've ever done in Schubert calculus, you can kind of just copy and paste it, and you can get the same kind of arguments working to show the exact same thing. So we have like the analog of Schubert polynomials that interact with some operations that are dual to them, and it's all a very nice cohesive story. Yes. Yes, there are pipe dreams. The pipe dreams, I've never successfully drawn one of our pipe dreams. Partially because it's, what's bad about it? It's not bad. Actually, it's the morally correct version of pipe dreams, I believe. Because it's the only model that computes triple Schubert polynomials if you set the variables correctly. So actually, we do have the only model that does that. We didn't write that down, but it does. So there's something nice about this. It does compute Schuberts. And I'll show you roughly what it looks like. So what it looks like is you have these doubled rows of boxes like this. And the default state of the model is you put pipes of different orientations inside every second row, which is why I can't draw it, because it's too confusing. So you would go like this, 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 and then you would put this, 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 and then you do this, this, this. Let me just do one more. This, 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 this. So this is the default state. And then what you do if you want to compute, so here if you want to compute these the analog of the Schubert polynomials that kind of govern our theory and are part of this rejection over there, you would put a t-tile into one of the boxes and then put horizontal lines everywhere above it. So for example, maybe there's a t-tile here. And you'll see why the horizontal lines are necessary is because then you break where these ambient pipes go. So really you have to extend it up like this. And then they, goes like this. And the rows have weights that look like xi minus tj and tj minus ti. There's some weird weights associated to it. But the point is you sum up all ways that you can create the same tree from filling this diagram with these t-tiles subject to these weights. And then if you want to do Schubert polynomials, you put like, I think you put 1, 2, 3, 4. And then if I want 2, 3, 1, 4 to pop out, you would put cross tiles in. And you would just demand that the pipes starting at 1, 2, 3, 4 go woo, and they zigzag down until they get to 2, 3, 1, 4 as the output. So it doubles up both for pipe dreams and for the forest polynomials that we compute.
So at a T, the labels are like 7, 7, and 7, or what?
Sorry, what?
The pipes at a T are all the same pipe number?
The pipes are all the same
At
pipe.
a T.
Oh, at a T. So so this wavy diagram, I guess the forest is telling you which pipes are merging. So like this T, you say like this pipe and that pipe merge. It's like the second and the third pipe merged and an output there. So this would be corresponding to the tree like this. So it'd be like the most basic tree. And you could create arbitrary binary trees by sticking in more T's. Yes?
What about K-theory?
Yes, K-theory works as well. So there's an equivariant analog. There is. But basically we have K-theoretic versions of these polynomials that are dual to the open cells. So the statement in the usual flag variety is that if I take the Euler characteristic of the structure sheaf of one of these Schubert cells, paired with the associated growth in the polynomial, W prime, this is either 0 or 1, depending on whether W is equal to W prime. So the growth in the polynomials are dual under the K-theoretic pairing of Euler characteristic to the open cells here. And similarly, we can write down these polynomials that have a nice combinatorial formula that are dual to the open cells, the open affine charts in our quasi-symmetric flag variety. And just to let you know, so the non-equivariant things are like not that bad. What they look like, if I want to create the forest polynomial associated to like this tree, what you do is you put inequality signs running up like this. You put strict signs going up like this. And you just take the generating function of all fillings of the nodes of the tree subject to these inequality constraints where the numbers on the bottom act like a flag. So here, these inequality signs would force this to be 1, this to be 1. This could be 2 or 3. So you get like x1 squared x2 plus x1 squared x3. So this is like the non-equivariant model. And then equivariantly, you would do this. And then in K-theory, you would also allow for some hacky thing that it also works out. Yes?
Can you
clarify, you said you could do it for at any type and for any Coxeter element C, but what depends on C and what doesn't? Like is QFLN, is this like a thing that is independent of C, or do you get a different definition if you change the Coxeter element, or sorry, different space, a different subvariety?
Right, so that's a good question. So I guess I'll tell you that, and then probably and I don't want to take too long. So the definition of a non-crossing partition, let me just quickly tell you how this works. So a standard Coxeter element is just the product of the simple reflections in some order. It doesn't have to be a nice order. I took a nice order, so I got the nicest thing, but you could take a random order, and this is standard Coxeter element. If you write it as a product of reflections, a non-crossing partition is by definition a prefix of a minimal length reflection factorization for the standard Coxeter element. So tau1, tau2, and tau1, tau2, tau3 would be non-crossing algebraic non-crossing partitions, and you run over all reflection factorizations of C. So not necessarily by adjacent swaps, because there aren't that many, but over arbitrary swaps, and it recovers this weird backward cycle thing when you specialize that particular C. So the things that don't depend on C are that the cohomology ring of the what we call the Coxeter flag variety is independent of C. So the cohomology ring itself is independent of C, and part of the reason for that is that the underlying GKM graph we're working with is the Carrera's lattice for C, and it's a classical fact that this is independent of the choice of C. They're all related by some conjugations. However, as algebraic varieties, these things are completely different. So, for example, if I take C to be S3, S2, S1, we get 5, I'll put in quotes, cube toric varieties, where we really mean iterated P1 bundle 3 times, which is it's just the face poset is the same as a cube, as not a cube, just like a trapezoid isn't a cube. It's like a trapezoid but in a higher dimension, higher dimensional trapezoid. Okay, but if I take the other C, then I get 4 cubes, and one of that beautiful drawing that Melissa drew earlier today of the tetragonal trapezohedron. Tetragonal trapezohedron, which is a horribly singular variety. So what ends up happening is that this horribly singular variety, you would think I could never compute the cohomology of a horribly singular variety. But what the construction gives is, even though the variety is singular, there's one magic point that's simple and smooth. That magic point is the highest point, and it corresponds to a lovely affine chart. Then all of the bad singularities are kind of handled by the lower toric varieties in this complex. So you never actually witness the horribleness of the toric variety, the individual toric varieties inside the whole complex, because the other toric varieties save you as you go lower and lower, which is odd. But yeah, we don't know what these varieties, are. So we do know what they are. They're the W inverse translates of Richardson's from W to WC. So union overall length additive factorizations, W times C, and you translate these Richardsons to the identity. There's a very nice reason that all the fixed points are non-crossing, but we actually have we have so little idea about their combinatorics. It took us like 30 pages to even determine that the top point after translation, the Bruhat maximum point, was the cluster, it was this non-crossing partition associated to the something called the Cambrian class. There's a lot of combinatorics that I can't tell you right now because it would take us forever. But
so we should take further questions offline.